Alright class, welcome back. We're still working on our points in our titration curve, okay? So in the last video we did strong acid, strong base. Strong acid, weak acid, okay? Now we're going to do strong base, weak base. Note here that our titration curve looks a little similar but different. We're now starting out high because we have our bases. So high pH, we're adding something like a strong acid, like hydrochloric, and as we add it, our pH is going to drop. Okay? We still want to be able to calculate our different points in our titration curve. Okay? So we're going to break it off again and do our strong base. Then we're going to come back and do our weak base. Okay? So our first point here again is still, we want to do that initial. Okay? What is our pH before we start? Okay? And right now we're going to talk about strong base. So before we start adding anything, this is a strong base problem, which they're really simple too, okay? Because really when we talk about strong bases, NaOH, KOH, a lot of our alkali earth metals are going to be strong bases. These are probably going to be the two that you're going to see most often, okay? So these break apart 100%. Okay, so you get your sodium, and then you get your hydroxide. Okay, so really to calculate this pH, okay, we're going to calculate POH first. Okay, that's just going to be the negative log of whatever the concentration is. Okay, so whatever our concentration of sodium hydroxide is, that's going to be our concentration of our OH. Okay, base problems, you get the extra steps. So to find pH, we often just say pH is 14 minus the POH. Okay, so easily calculate your POH, then go through and say 14 minus pH, or POH will get you your pH. No problem. Okay, that's the initial. Okay, now this is before the equivalence point. Is the next point we want to look at. Before our EQ. Okay? With a strong base, strong acid, they're not going to form a buffer because the reverse reactions don't occur. Okay? So in this case, we just need to figure out how much of the strong base we have left. Okay? And what's its concentration. Okay? So really we want to take our concentration of our OH times whatever volume we started with. Okay? And then we want to subtract out how much was neutralized. So what is our concentration of, say, our hydrochloric acid times how much volume of that we've delivered. Okay? That will really give us the moles of our base that are left over. Then we just simply want to divide that by our total volume. Okay? That's the volume of our base plus the volume of our acid. Okay? This is our X. And then we just want to take the negative log of that whole thing, and remembering that's going to be your POH. So then pH, again, is just that 14 minus your POH. Okay? So find out how many moles of base you still have left. Divide it by the total volume. If you take the negative log of that, that's going to get you your POH, and then say 14 minus your POH, your pH. Should be fairly straightforward. Okay. Now let's go to number 3, because this is at the equivalence point. Guess what? We got another easy one here for you guys. Okay. So strong acid reacts with a strong base, or strong base with a strong acid. Those reverse reactions don't occur, which means we don't really have a conjugate acid or base present. All we have is water present. Okay. Which, if all we have is water present, then we should know what the pH is for water. The pH is 7. Okay? So for a strong acid, strong base, or strong base, strong acid titration, the pH is going to be 7. Perfect. Okay? Now let's look at number 4. Okay? So this is after the equivalent point. Okay? At this point, we've neutralized all of our base. Okay, all we have is excess strong acid present. So all we have to do is figure out what is the concentration of that acid, and because it's a strong acid, all we have to then do is say take the negative log of that. That will give us our pH. Okay? So to find out how much acid is left over, we're going to take our concentration of acid, okay, times how much volume of that acid we delivered. And in this case, we're going to subtract out how much was kind of lost from neutralizing with the base. So times the volume. Alright? And then we're going to divide that by our total volume. Alright? That's going to give us our new concentration for the base. Okay? We'll call that, we'll call this after. Alright? So once you have that after, then you just simply take the negative log of that concentration of your acid that's left over. Alright? That is your pH. Okay? So find out how much is left over beyond just the equivalence point. Then divide that by your total volume. That gets you your concentration of your strong acid that's in the actual solution. Take the negative log of that. That will get you your pH. So this has been a calibration curve with a strong base with a strong acid. We're going to come back in just 1 second after I reset and do a weak base with a strong acid, and we'll calculate these different points again. Okay? So hold on for part B. Alright, so now we're going to work on a weak base being titrated with a strong acid. Okay? Weak bases are a little bit harder to identify. A lot of times we have a nitrogen involved. So like your ammonia, your NH3 would be a weak acid. I mean a weak base. Okay? If we added a proton to it, then it would be a weak acid. Okay? So anytime you see a nitrogen, think that that actually could be a weak base. Okay? So we're going to go through our different points in terms of finding our pH. Okay? So here again we got the initial. Okay, before we start our titration. So this is a weak base problem. Okay, so we remember our shortcut with acid. We can apply that to our base. Okay, so we're going to say X is going to be equal to our Kb. That's what we're talking about a base. We want the Kb times that formal concentration for the weak base. Okay, that should be the same as whatever they tell you in the problem. Okay. Now realizing your X is times your OH concentration, so if you take the negative log of your X, that's going to get you your POH, and then your pH is going to be that 14 minus your POH. Let's write that bigger so you guys can see it. Okay? That's the initial before we start. Okay? Just a weak base problem. We can do our shortcut for base. X is equal to the square root of Kb times the formal concentration. That gives you your hydroxide concentration. From there, take the negative log of that, gives you pOH. 14 minus the pOH is your pH. Alright, now we're on to number 2. So this is before we get to our equivalent point. Before our EQ. Okay? Now we've added some hydrochloric acid. Okay, we've neutralized some of the base. Okay? And in this case, we take our ammonia, add hydrochloric to it, or just proton. That's going to give us some of its conjugate acid, ammonium. Okay? So ammonia and ammonium. So these are conjugate pairs. So guess what we have going on now? We have a buffer. We have our conjugate acid. So really we're talking about we have our buffer present. Okay? What equation do we use for buffers? Henderson-Hasselbalch. Okay? So this says our pH is going to be equal to our pKa plus our log of our acid, our base over our acid. Okay? Now, let's talk a little bit about this. So, a lot of times in these type problems, you may have been given the Kb. We need the Ka here. Okay? So remember our relationship between Ka times Kb equals our Kw for water, or your pKa plus your pKb equals 14. Okay, both of those relationships hold. Okay, so if you know the Kb, then you know your Kw is a constant. You can find your Ka. You can plug that into your negative log of your Ka is going to be that. So now you need to actually set up your ratios. Okay, and this is going to be your base. That's going to be the acid. Okay, so it's going to be flipped a little in terms of the calculation. Okay, so I'll get back to the kind of the simple method. So if we're talking about finding our concentration for our acid, our base in this case, okay? So in this case, some of it has been neutralized, okay? So we want to start off with what was our initial concentration, okay? Times how much of that did we start with, okay? Then we know some of it has been reacted with the acid, so let's put in its concentration for that hydrochloric acid times the volume that we've added so far. Okay, that will give us how many moles of our base are present. Okay, and in this case, HA, or our acid, is simply how much of it has been converted. So that's just our concentration of our acid times the volume that we've added for that acid. We divide those two, take the log of that, that will solve our problem for us. That goes in terms of moles of our base over moles of our acid. Okay? Now, the shortcut in this method is, like I said in the other video, is a lot of times these concentrations will be at the same, 0.1 molar and 0.1 molar. So if we know that the equivalence point, let's just say we started with 25 milliliters. So let's just say we did 25 last time. Let's say 50 milliliters. So our equivalence point was at 50 milliliters. Okay? And they're asking, what is our pH when we get to 10 milliliters? Okay? So if I wanted to, we've added 10 milliliters, let's say, our hydrochloric acid. Okay? So if I wanted to set up this ratio, and I know that my equivalence point is at 50 milliliters, then really this is our 50 minus our 10. That's how far we've gotten to the equivalence point, over my 10. Or this is 40 over 10, or 4 over 1. Okay? That's how you can just use your volumes instead of the moles. Okay? That's if the concentrations are the same and you know what the equivalent volume is. So sometimes it's helpful to go ahead and figure out what the equivalent volume is, so you can figure out these ratios for your Henderson-Hasselbalch equation. Alright? But this is the more rigorous method. This will always work. Okay? Now we're up to 3. Okay? So this is at the equivalence point. Okay? So think about what's happened now. Okay? So at the equivalence point, we've added enough acid to neutralize all of the base. Okay? Which means that base has been converted all into its conjugate acid form. Okay? Which means for this problem, it's a weak acid problem. We just got to figure out its concentration. So for weak acids, with our shortcut, okay, we say X is equal to our Ka times that formal concentration. So hopefully you've already figured out how to find your Ka value. Okay? Now we just need to figure out what is that formal concentration. Okay? Which all we have to really do is account for the dilution. Okay? So figure out how many moles of our starting base we had. So what's its concentration times that volume. Okay? That gives us the number of moles. All of those moles were converted to the acid from the base. Okay? Then all we have to do is divide by our total volume. Alright? So that's the volume of the base we started with the volume of the hydrochloric acid we've added. Okay? That's going to be my formal concentration. So then if we take the negative log of our X, that's going to be equal to our pH at the equivalent point. Because we do have a conjugate acid here, then for this titration, the pH is going to be acidic. It's going to be below 7. I did mention this in the other video, but for a weak acid versus a strong base, you have the conjugate base present. Okay? So its equivalent point is going to be above 7, because all you have is the conjugate base present. Okay? But in this case, you have the conjugate acid, so it's going to be below 7 because it's an acid. Alright? Now, our very last, our final point after the equivalent point. Alright, after EQ. At this point, we've neutralized all of the base, and all we have is excess strong acid. The strong acid will kind of overwhelm the weak acid, so we can pretty much just focus on how much strong acid have we added. Okay? So, we pretty much know that just the negative log of whatever that acid concentration is going to be equal to our pH, because it's a strong acid. Okay? So all we have to really do is figure out that concentration. Okay? So really we want to take, in this case we were using hydrochloric, so take its concentration times how much we've added. Okay? Some of that was neutralized with the base, so let's find out how many moles of that base we used. So minus NH3 times the volume of NH3. Okay, that would tell us how many moles of the base, and then subtract that from how many moles of your acid. That will get you how many moles of the acid are still left, and then this is just divided here again by the total volume. Alright, that's your concentration. You can take the negative log of that. That will get you your pH after the equivalent point, which, since it's acid, excess acid here, should be fairly low in terms of our pH scale. Okay? I hope you've enjoyed these. If you have any questions about calculating these different points, please feel free to let me know. We're going to try to work some more actual problems on these in terms of the recitation next week. I think this Friday is Good Friday, so I hope you guys have a good holiday and everything, and we'll see you soon. Bye.